5.5 is conditional probability. So what we're doing in this section is we're trying to understand and solve problems that involve dependent set events. So if you think about if something is dependent, then that means one thing has to happen in order for another thing to happen when we're talking about events. So it says a dependent event is events whose outcomes are affected by each other. For example, if two cards are drawn from a deck without replacement, the outcome of the second event depends on the outcome of the first event, which was the first card drawn. So if you pull a card from a deck and don't put it back, then that means you have one last card to select from when you do the second selection. Conditional probability is the probability of an event occurring given that another event has occurred. So it's saying, okay, in the first time I picked this, so in the second event, this will happen because I did the first thing. So we're taking a look at a situation here where we're drawing two balls from the pot without replacement. So it says a ball is randomly selected from the pot and it is not replaced. Then a second ball is drawn. So it says define the following events. A is that the first event A is the first ball drawn as white, and B is that the second ball drawn is white. So if I take a look at the pot here with my two white and one gray balls, then what I'm saying is if event A were to happen, so that is a probability of selecting a white. So this is A, this is not A. So probability of selecting a white ball would be 2 out of 3. Probability of not selecting a white ball on your first selection would be 1 out of 3. So probability of A happening, you have a 2 in 3 chance of that happening. So then B, the next part says, what is the probability given that the first of B happening, given that the first ball drawn is white? So if you've drawn the first ball and it's white, what is the probability that the second ball drawn is white? So if I take a look at it this way, so this is event B happening, this would be not B happening. So if I've already taken one white ball out, what are the chances now of me selecting a ball that is white on the second time? Well, there's only 2 balls left. One is white, one is gray. So I have a 1 in 2 chance. Probability of not getting a white ball in that second one is 1 gray out of the 2, so it would be 1/2. So on the other end, if on that first selection I didn't get a gray ball, so that would mean, I didn't get a white ball, that would mean I got a gray ball, then for event B to happen, which would be that the second ball is white, well, given that I didn't select a white ball in the first one, I have 2 white balls left and I'm going to pull one of them. Well, I have a 2 out of 2 chance, so that would be probability of 1. You have to. If the only thing left is white balls, then that means that's what you're going to get. So what are the chances of not getting a white ball in that second selection? It's like I said, there's only 2 white left, so I have 0 chance of not selecting a white ball. So the probability of B happening, given that the first ball drawn is white, so I'm looking then at this side here. So given that highlighted side, the first ball drawn was white, was 2/3. So once I've taken that selection out of there, the probability then of that second ball being drawn that it's white is 1/2. Probability of A and B. So A and B is that intersection, and also means that we multiply. So probability of A happening and B happening would be 2/3 times 1/2. So that is, not a 3, sorry. Why isn't my math working? 2/6, so it's 1/3. So you have a 1/3 chance that the first ball and then the second ball drawn are both going to be white. So the next part here says events A and B are dependent because, so why are they dependent? It's because the outcome of the second event depends on what happened in the first event. So if we take a look at our tree here, this happening depended on what happened there. This happening depended on what happened in that first one. So they are dependent because the outcome of the second event depends on the outcome of the first. So that, by definition, is why this would be a dependent event, because we didn't replace it, so depending on what we selected the first time was going to impact what we selected the second time. So what happens then if you do replace that ball? So it says the ball is randomly selected from a pot, but then it's put back and a second draw is made. So how does that affect then the probability that the first ball I get is white and the probability that the second ball I get is white? Okay, so the probability for A happening and not A happening. So probability of getting a white ball is still 2 out of 3. Probability of not getting a white ball is still 1 out of 3. For the second event, so that's the B, and then our B not happening, if I've put that white ball back in there, then for the second event, I've still got the same sample space. There still is going to be a 2 out of 3 chance that I get a white ball on that second selection, and there still will be a 1 out of 3 chance that I get a not white ball, or in this case a gray ball, in that second event. So what happens if the first time I selected the gray ball? So I select the gray ball, but I put it back in. So I had a 1 in 3 chance of getting the gray ball. I put it back in. So what is the chance that I will get a white ball the second time I select? And what is the chance that I won't get a second ball the second selection that I make? So again, I'm back to my 3. So chances are that I have a 2/3 chance of getting that white ball the second time I do the draw, and I have a 1/3 chance of not getting the white ball the second time I draw. So probability of getting A, first ball is white, 2/3. Probability that I'm going to draw a second ball, or that the second ball I draw is white, given that the first one was white, is, again, 2/3. Because I put the ball back, doesn't affect it. Probability of A and B, so that means I have 2/3 for the 1 times 2/3, remember that and means multiply, is 4/9. So it says events A and B are independent because, they're independent because what you did in the first one didn't have any impact on what you got, or what the result was in the second one. So they're dependent because the second event, or your outcome, I guess, I should write that, the outcome of the second event does not depend on what happened in the first event. Okay, so just kind of summarizing this together. Probability of events A and B. So in general, probability of A and B happening, if I look here, A and B gave me the probability that A happened times the probability that B happened given that A. And we write that as B/A. So that's what that slash means. Not to be confused, and if you look in the textbook, B B not A was what we were looking at before, was slanted. B given A is straight up and down. So this is B not A, and this is B given A. So you just have to watch what you're doing there, because one is slanted and one is straight up and down. So this would be A happening, this would be B happening. So probability of A and B. The equivalency of that then, of probability of, probability of B not A happening, if I look at my chart here, is that probability of A intersection B, so that's that part. But I'm dividing out that probability of A. So it says, note, events A and B are independent. So that kind of went wonky on there. Events A and B are independent if probability of A given B, probability of B given A is equal to just the probability of B happening. So we know that they are independent events, meaning that the one doesn't matter what happened in the first, because the second one isn't affected by it, is just given probability of B. So that's the second one. That's that with replacement one. Nope. So that is this one right here. So it's for independent events, probability of A and the intersection with the probability of B is equal to probability of A times the probability of B. So if they're independent events, so that's that with replacement is where you're going to see independent events. Most of the time, there'll be some other situations. Then if you're looking at the probabilities of the intersection, it's going to be probability of A times probability of B. Okay, next example. 2 cards are drawn without replacement from a shuffled deck of 52 cards. Define the following events. So this is without replacement. So if it's without replacement, that means we're not putting it back in, so that means what happens in the second selection is going to depend on what you took out in the first. So that means that these are independent events. Sorry, they're dependent events. I said that wrong. So that means dependent. So because they're dependent events, then that means the probability of A intersect B is going to be the probability of A times the probability of B happening given that A has. So probability of A, first card is a face card in a deck of cards, if you remember, so that's king, queen, and jack, and there's 4 suits, so there's 12 out of 52. Probability of B then, I have taken one of those out of there. So that means that I'm one less face card and one less card in total. So probability of B given A means that there are 11 left for me to choose out of the 51. So when I multiply this, this is equal to 11, or reduces once you multiply, over 221, which as a percentage would be 4.8%. So B part says, what is the probability of A not happening and B happening? So again, these are, you're not replacing, so that means that they're dependent on each other. So we're looking at the probability of A not happening times the probability of B happening, given that A did not happen. Probability of A not happening. So probability of the first card not being a face card. Well, if 12 of them are face cards, then that means there are 40 that are not going to be face cards. So if I've taken out one of those cards, I know that I'm going to be left with 51 cards. But probability of B happening is that that second card is a face card. So that means I haven't removed a face card because the first one wasn't. So I have 12 to select from. So this is the equivalent of, if I reduce it, 40 over 221, which is 18.10%. So 18% chance that your second card is going to be a face card, given that your first one wasn't. Example 2. According to a survey, 91% of Canadians own a cell phone. Of these people, 42% have a smartphone. Determine to the nearest percent the probability that any Canadian you meet during the month in which the survey was conducted would have a cell phone. So let's first identify the event. So probability, or we'll call C, the event that the person owns a cell phone. So we'll call event S the event that the cell phone they own is a smartphone. So we know from the information here that the probability of a person having a cell phone was 91%. And then we know that the probability of the person owning a smartphone, given the fact that they own a cell phone, so that's probability of S given C, is 32%. So this is 0.91, this is 0.42. I have to sneeze again. Okay, so what we need to know here then is, based on this information, is that smartphones, if you did this in the diagram, smartphones are a subset of cell phones. So what that means is that the probability of having a smartphone is equal to the probability of a smartphone and a cell phone, which is also the same as saying the probability that if you have a cell phone, you're going to have a smartphone. So the question asked, what is the probability that any Canadian you meet is going to have a smartphone? So the probability of them having a smartphone then is the same as the probability that they have a cell phone and a smartphone. So that's because these are not independent of each other. In order to have a smartphone, you have to own a cell phone. So that's where that subset part comes in. So we know that they are not mutually exclusive. Then the probability of owning, this is going to be the probability of owning a cell phone. Whoops, did that again. Times the probability they have a cell phone, a smartphone, given they have a cell phone. So probability of them having a cell phone is 0.91. Probability of them having a smartphone given they have a cell phone was 0.42. So this equals 0.3822. So that's 38.22%. So the probability that a person has a smartphone then is 38.22%. Next one. cards are drawn without replacement from a shuffled deck of 52 cards, what is the probability that both cards are hearts? So if I think of this as the tree diagram, we've got our 52 cards here, okay? So probability of a heart, probability of not a heart. So probability that the first card drawn is a heart would be 39 out of, sorry, not, I did that on the wrong side, that should be 13, because there's 13 hearts in a deck. So 13 out of 52. Probability of not getting a heart would be 39 out of 52. Now we're not putting these cards back, so in our second attempt, we have a heart and not a heart. So if I've selected a heart the first time and I'm not putting the cards back, then that means I have a 12 out of 51 chance of getting a heart. And if I didn't select a heart, if I had not a heart the first time, so then that, or a heart the first time, then not a heart the second time, that means there's still 39 of the other cards, but 51 out of a total of 51. So if my first attempt was not a heart, then that means in my second try, I have 13 cards that are hearts out of the 51. And for the second one, if the first one wasn't a heart, then that means that there's only 38 not hearts left out of the 51. Okay, so what is the probability that both cards are a heart? So this is saying what's the probability of heart the first time and a heart the second time? Well, because this is without replacement, then we know we have dependent events. So we're looking at probability that the first one is a heart times the probability that the second one is a heart, given that the first one was a heart. So if I take a look at that then, for probability of it being a heart the first time, that was 13 out of 52. The probability the second time that it was a heart, given that it was a heart the first time, is 12 out of 51. So when I multiply and divide, I'm left with 0.588, which is 5.88%. So what is the probability that neither card is a heart? So that's probability that the first card is not a heart, and probability the second card is not a heart. So that's, if we expand it, with probability of the first card not being a heart times the probability that the second card is not a heart. Oops, given that the first card was not a heart. So if I take a look at my numbers here, probability that the first card I selected was not a heart was 39 out of 52. Didn't replace anything, so the probability the second card is going to be a heart, given that the first one wasn't, or was not a heart, given that the first one was not a heart, is 38 out of 51. So I'm looking at my two X'd out hearts here. So when I multiply then divide, I am left with 0.5588. So that is 55.88%. So what is the probability that exactly one of the two cards is a heart? So that means what we're looking at is the probability that the first card is a heart, but the second wasn't. Or the probability that the first was not a heart, but the second was. So probability that if I say the first card was a heart, I have a 13 out of 52 chance of selecting that, and I have a 39 out of 51% chance that the second one is not a heart. So that's looking here. First one was a heart, 13 out of 52. Second one not a heart, 39 out of 51, because I only want one heart. Or I could have gone the other way, so that or is that plus. What happens if my first one was not a heart? So if that's not a heart, there was 39 out of 52 there. And then that would mean my second one has to be a heart, so that was 13 out of 51. So this one, if you multiply and then reduce, you are left with 13 out of 68 plus the second one when I multiply and reduce, because basically I have the same numbers. I'm multiplying 13 times 39 on the top for both and 52 times 51 on the bottom, so that is 13 out of 68. So 26 out of 68 is 0.3824, which is 38.24%. So I have a 38% chance of getting at least one heart out of there. Okay, well, let's change it up and say, what are the probability that both of the cards that I select are an ace? So that would be the probability of the first card being an ace and probability of the second card being an ace. So again, these are not mutually exclusive, they're dependent events. So the probability of the first card being an ace times the probability that the second card was an ace, because it says both cards, given that the first one was an ace. So if I think about my deck of cards, I have 4 cards, or 4 aces in the deck, so that's a 4 out of 52. If the first card was pulled out, then that means I'm left with 51. And if the first one was an ace, then that means that there are only 3 aces left in the deck. So I have 4 times 3 over 52 times 51. Well, that reduces to 1 over 221, which is 0.0045 or 0.45%. Okay, last example. A company has 2 factories that make computer chips. Suppose 70% of the chips come from factory 1 and 30% come from factory 2. In factory 1, 25% of the chips are defective. In factory 2, 10% of the chips are defective. So A part says, suppose it is not known which factory a chip came. What is the probability that the chip is defective? So what we need to do then is we have to figure out what's the probability of them being defective in A and the probability of them being defective in B. So if we do the tree for this, we have factory 1, I'll call it F1, and factory 2. So 70% of the chips come from here, so that's a 0.7. Go to factory 1. 30% then are from factory 2. So in factory 1, 25% of the chips are defective. So that's, we think of this being as defective and not defective. We have a 0.25% there. So that means you have a 0.75% or 0.75 or 75% chance that they are not defective. In factory 2, if we look at defective and not defective, chances of them being defective in factory 2 are 10%. So that means the chances of them being not defective is 90%. probability of them being defective, we have to look at what's defective in factory 1 and what's defective in factory 2. So factory 1, we have 0.7% of the chips coming there, and then that means 25% are defective. So because of that and, we multiply. Or we have, so because we're looking at an or, that's a plus, or from factory 2, we have 0.3% of the, or 0.3 of the chips coming. I keep saying percent, but I've changed it to a decimal. So 0.3 of the chips come from there, and of those being defective, 10% are. So factory 1 and defective is 0.7.25, or times 0.25, so that is 0.175. Can't read my own. Pretty sure that's what I wrote there. And then the amount that would be defective from factory 3, 0.3 times 0.1 is 0.03. So if I add those two up, I have 0.205. So I would have a 20.5% chance that the chips that I get are defective. So it says, B part says, suppose a defective chip is discovered, what is the probability that the chip came from factory 1? So we're looking then, trying to find out what is the probability that our chip came from factory 1 given that it is defective. So if I look at this, because they are dependent events, probability of F happening, so factory 1 happening given factory 2, or that they're defective, we can use that formula that I gave you at the beginning. So probability of them being from factory 1 and defective, or defective and from, I'm going to write it the other way. Probability of them being defective and from factory 1, and we divide that by the probability that they were defective. So we know that they're defective. That's the given part. So then that's the part that goes in the bottom. The probability of them being defective and from factory 1. Well, that was 0.7 times 0.25. So that was this right here. We're from factory 1 and defective. Probability of them being defective. Well, we figured that out here. Probability of a chip being defective was 20.5 or 0.205. I'll finish this up here. So this is equal to, oops, that was a bad equal sign, 0.8537. So that is 85.37%. So probability that they were defective and came from factory 1 was 85%. So some key ideas. Probability of one event depends on the probability of another, means that we have dependent events. So for example, drawing a heart from a deck of cards and then drawing another heart from the same deck without replacing the first is a dependent event. If event B depends on event A occurring, that's called conditional probability that event B will occur, given that event A has occurred. And we can write that as, so if it's a dependent event, we can write that B but not A, or sorry, B given A as a probability of A and B happening divided by the probability of A. Another thing to remember is if event B depends on event A in the following then the probability that both events occur is equal to the probability of A times the probability of B happening given that A has. That tree diagram is helpful in figuring out those calculations. You don't necessarily have to use it, but it does make a nice picture for you to see what you're working with. Drawing an item and then drawing another item without replacing the first item results in a pair of dependent events. Here's your assignment.